effective drug concentration expression on epinephrine dosing errors. So some, I guess, some people aren't used to, maybe it's molality, or maybe it's weight percent. I don't know. I have to dig into that article to see what the heck it was. That people, the type of concentration unit people weren't quite understanding. But it happens, right? And high concentration errors. And it's expressing the concentration of a solution. It's important in doing it right. Not only how to make the solution, but in saying what something is. Okay. So Lauren, what is the difference between a solute and a solvent when referring to a solution?
So like the smaller one part.
That's exactly, she said it exactly right. The solute is the one that's in the smaller amount. Right. They could both be liquids. Fine. It's just that the liquid that's in a smaller amount is the solute. The one that you have the most of is the solvent. Yeah. Okay. Let's take a look at the the atomic level. Sodium chloride, there's no molecules. What's going on at the atomic level when sodium chloride dissolves in water? Okay, let's take a see the picture here. Okay, here's the static image. Now, Victoria, where are the water molecules? Yeah, they're gonna be floating around. Is water a polar molecule, Brandy? Is water a polar molecule? It is. Well, sorry, now she changed her answer. You're right the first time. It is. Why is it a polar molecule? It's bent. All right, it's bent. You've got the oxygen. All right, go back where I can write somewhere. You got the oxygen. You do a Lewis dot structure that's lone pairs. That's why it's bent. But polar means I'm supposed to say a little partial. One end's partially negative. The other end is partially positive. What end is kind of negative on water? Where would it be, Albert? Where would this negative kind of rear end be? On the O, because O is more electronegative. Or O is more electronegative. So you're supposed to say partial negative here, and maybe little partial positives on the hydrogens or something, right? Partial is this guy, right? Okay. So let's take a look what happens when you dissolve sodium chloride in water. So little water molecules are floating around doing their thing, and you see the crystal of sodium chloride there. And what's happening, right? You see this? All right, there's something going on there. And then this guy, let's pause him. Something going on here too, right? So the water molecules are pretty much decomposing that crystal of sodium chloride. So can you tell, though? Eric, this is supposed to be called hydration, by the way, of water going around these ions and orienting themselves in different ways around ions. It's called hydration. Which one is which? Is the little green sphere or the little black sphere? Which one is sodium? Right? Because one has to be sodium ions. The other one has to be chloride anions. Which one is the sodium? Now you're right, but why? He's right. The gray one is the sodium ions. But why? Because of the O's. That's what I'm thinking too. Because look at those O's. Those O's are partially negative. They're all oriented towards something positive. And then look at the green sphere, right? All those little hydrogens, which have a partial plus, are oriented towards something negative, the chloride anion. So that green is the chloride anion, right? The greens are the Cl chloride anions, and the grays are the sodium cations. So one of the next questions are going to be draw these hydrated images. So when you draw it, just draw a circle for the sodium, right? Na+, and then orient the water so that the oxygen is all pointing towards it, right? Here, sketch a hydrated sodium ion. So Draw your sodium ion. Then you have to draw all these bent water molecules, but have it so that the oxygens are all butting up against it, right? Kind of like this. You can squeeze in as many as you can, okay? And then do the same thing for the chloride anion. Draw its hydrated image. So you draw, same idea. And draw a bunch of water molecules around there, but this time the hydrogen atoms have to be orienting themselves towards it. And draw a bunch of water molecules around the chloride anion. That's called hydration, or solvation, or dissolving. Same kind of idea, I guess. But this is the end result, are hydrated ions. Well, you can, but you don't really have to, right? You can, if you put them in, it'll help you remember a month from now what you just did, right? Why you did it that way. Jessica, suppose we didn't have Na+. Suppose we had iron +2 or iron +1 in water instead. Which one would be more strongly hydrated in water, and why? Fe1? Why? What's causing the hydration? It's the polarity, the charges, right? Now the water doesn't have full charge, it has this partial negative charge, but still it kind of has a charge going on there. Then you have these cations. So you have a negative dude, he's sucking up with the partial positives for the chloride, but if you had Fe+2 versus Fe+1, which one would water probably be squeezed up even more tightly on and even going out in those big hydrated spheres they're starting to talk about and things? It gets complicated. +2, the one with the higher charge. Because there's a stronger interaction, because that's what's causing the interaction in the first place. It's not a bond, it's just like an interaction kind of thing, kind of like sucking up to it. Okay, so definitely Fe+2, it's just because of the charge. You have a saturated solution of sodium chloride. Okay. Saturated. What's saturated, Cassandra? Okay, now picture the movie we had before. Picture this movie. Okay. If it was saturated, how would this movie change? What is saturated? Just means it can't dissolve anymore. That's what saturated is. It's just you can't dissolve anymore. It's full. How would this image change? Right? Because if it's dissolving more, that crystal is going to keep disappearing on you. But if it's saturated, the crystal can't be disappearing. But you can't stop the movement. What's that? Well, the water is going to still be ripping off the ions. Yeah. We're close. So close. You're going to have all these, you're right, you're going to have all these hydrated ions around here, but you can't stop the dissolving. It's still going to come up here and pull some off. It's just that it has to redeposit them back on again. And they know that happens because you get new surfaces, fresh surfaces. So it recycles. So the movie isn't as great as it should be, but it does an okay job. So you're going to have your dynamic equilibrium, it's called. It goes both ways. It's dissolving and it's precipitating out, but at the same rates. So we have our water and we have our ions. Okay. Now, water's coming along. See, it pulls them off, but it's also depositing them at the same time, at the same rate. So it's the movie doesn't show near enough or long enough, but the rate that sodium is being torn off is the same as the rate as it's being precipitated back. So the rates are the same. And they call it dynamic equilibrium, I guess, would be the best way to describe it. Supersaturated solution. Well, if something is saturated, that means it can't dissolve anymore. Supersaturated means it dissolved more. But we just said it can't dissolve more. So how? It's a very peculiar situation. But when you start dealing in the microscopic world, you can get some really weird properties. Supersaturated solutions is one of them. Okay, I wish they didn't skip all this pre-story I have to tell you, but I have to tell you the pre-story. You have a, what type of flask is that called? Erlenmeyer. They have an Erlenmeyer flask, they put some water in it. And then that white solid, they dumped a bunch in and got as much as they could to dissolve. And then they heated it up. Now it will dissolve. Will it dissolve more? Yeah. Because what happens is higher temperature. Things just speeds up. Things speed up. Things move faster. You can fit more in there. So it'll dissolve more. They heat it up some more. They dump some more in, right? So this thing is really, it's pretty hot, and they dissolved a lot in there. And then they set it on this bench, and they didn't touch it. And they let it cool down really nice and slowly. And they had to make sure there's no floaties in there, and everything is super clean. And just don't jiggle the flask or anything. It's very touchy. So this is what's going to happen. So they made a supersaturated solution of sodium acetate by heating it up, and that's the result right here. And what they're going to do is they're going to take one little crystal. Now this is of more sodium acetate, but it doesn't have to be. They could take a little hunk of dirt. They could take a little piece of wood. They could jiggle the flask, whatever they want, and this is what's going to happen. They're just going to drop a little particle in there. We call it a hygroscopic nuclei, but there it goes. Everything's just precipitating back out again. So it's a very supersaturated solution. So much was in there, the thing looks solid. Okay. Now, Bill Nye, the science guy, is still around. Saw him on TV. And I'm pretty sure I saw this from Bill Nye, the science guy. The idea is how to make a cloud. And the reason why I'm showing you this is because they believe to make a cloud, you need a supersaturated region of air. And the hard part is you can't see it. I mean, once I dumped water in here to make a cloud, I need water vapor. It's there. I mean, it's there. So you can't see it, but it's there. And we need wind. We need a pressure difference. So I'll get some wind going here. And there's not much there, right? Maybe you might see a little white thing, but there's not much. You need hygroscopic nuclei. So we'll add some hygroscopic nuclei. You need something for the little tiny water droplets to grab onto it and to make a droplet in the first place. So get a match going nice and good here. Plop it in. See the little puff of smoke? If you did or not, you'd have to believe me. There was a little puff of smoke. Did you see it, Alyssa? All right. See the advantages of sitting up front? There is, right, Summer? So the smoke is going to be my hygroscopic nuclei. It was missing before. A cloud. So that means to make a cloud, well, go back this way. Think of it this way, a raindrop. The heck? Look at that. Soot. You have snowflakes, raindrops, hailstones. Look at all this stuff. All right? There's a hygroscopic nuclei inside each and every one of those. But what is it? Is it smoke? Is it a dirt particle? A dust particle? It'd be a really... I can smell the match already. So it's definitely not smoke, because we'd be living in a really dirty world if it was smoke. Not dust either. Anybody know what it is? Every raindrop, every snowflake, every hailstone, everything is a little piece of what? Our world is covered by 3/4 of this stuff. Ocean, right? Ocean has a lot of what in it? Salt. So the sun shines down on the ocean, and what happens? It evaporates, right? So where's all this salt go? It just gets picked up in the wind. Probably most of it blows back in the ocean, but it gets picked up in the wind. Inside every little raindrop, every little snowflake is an extremely small, what? Crystal of sodium chloride. You're drinking salt water when you drink a raindrop. You just can't taste it. Right? Okay. However, the real meat of what we're concerned about today is solutions and concentrations. And I'm going... Acid rain is just what dissolved in water. Carbon dioxide, carbonic acid. Same stuff as what's in soda, carbonic acid. It's a lot more carbonic acid because they pumped in CO2, right? Psh, you pop the can open, it's just carbon dioxide shooting out of there. So, but yeah, come on. Though everything is on a scale. So what's really, really bad versus what's really, really good. There's stuff on this benchtop right now that'll kill you. But it's at such a low concentration, nobody cares. We don't even test for it. Right? So it's true. Whatever doesn't kill you makes you stronger. It really is true. Okay, this is what we're worried about. Now, I'm going to give you these definitions, right? Below info given. Okay. Now, my strong suggestion is to treat this as algebra. And I look at each one of these definitions as an equation. I think it's so much easier if you can look at it that way. Let's pick on somebody here. Monica, let's just pick this one right here. How many things could change if you can visualize that as a mathematical equation, as an algebraic equation? How many things can change? How many things do you think could change in that equation? I see 3. Does everybody agree 3? Yes. Yeah, there's 3 things, right? 1, 2, there's 3 things that could change. How about the other equations? It's always 3 things. That means it doesn't matter how wordy the question gets, how many things or parameters, Ramiro, are they going to give you? They're going to give you 2, and you're going to solve for the 3rd. That's the name of the game every single time. Except sometimes it's going to look confusing. Because they might ask for grams of solute. Let's say you're going to use this equation. They give you 2 out of the 3 you need, but they want grams. Well, you're pretty much going to have to solve for what? Moles, and convert to grams. How do you convert from moles to grams? Not mole bridge, molar mass. Molar mass, right? Add everything up from the chemical formula. I guess it's technically a molar bridge too, I guess, right? But I'd like to think of mole bridge as that chemical reaction kind of thing. Okay, so that's the game we're going to be playing. Let's try one of these. How would you prepare? Now, let's not worry, Mari, about the how would you prepare part. We'll answer that later. Okay? So we'll answer this part later. First, take a look at this question. Tell me which one of these equations do you think we should be using? Let's number them. 1, 2, 3, 4. Which equation should I be using? Which equation best applies? What would you say? Don't worry about the how would you prepare part. I hear a lot of 2s. Everybody agree? 2s? It's the only one that has a percent in it. That's kind of what I see as a hint. Right? It's the only one that has a percent in it. So I would say use equation 2. Okay, so mass percent has to be mass of the solute all over total mass. Doesn't matter the question. They had to have given us 2 things. We're going to solve for the third. Maria, what's one of the things that they gave us? 10% is the mass percent. Leave the percent symbol out. Oh, I forgot my times 100, didn't I? Leave the percent symbol out, otherwise you're going to push it on your calculator and just really messes everything up. All right? 10. We need one more. Caroline? The 250 is the what? She says total mass. You agree? 250 is the total mass? Yeah. Because look at it, it says 250 grams of an aqueous solution. Right? That's the total mass of this stuff. That's the total mass of the solution. 250. We need mass of solute up here. Okay, now we have to remember how to do our algebra. A over B equals C over D. Let's do an easy one first. How do you solve for A? Yeah, multiply the B and the C, right? It's that diagonal story, right? If you want to move from one side to the other, it has to go along the diagonal. If you want to solve for the A, the B has to go up there with the C and leave the D alone. Right? You have the CB over D. If you wanted to solve for D, though, let's pick a different one. You want to solve for D. If you want to solve this for D, you got to move the D where? Where the what is? Where the A is. Get rid of the A. Then you have to get rid of the B. So move the D where the A was. Right? Get rid of the B. Move him where the C is. Get rid of the A. Move him down there. BC over A. Okay. If you see that, you know how to solve for the mass of the solute then. It would be what? Lauren. It would be what? How would you calculate it? What times what divided by what, whatever? Okay, yeah, the same. 10 times what? 10 times 250. Keep going. Then what? The 100's up on top. Go along the diagonal. Has to bring it to the bottom. Right? See the diagonal? Right? 10, that's pretty much just 25. I can't. Okay. We're close. We're supposed to do the how would you prepare part. Now, what should be the units on my answer there? Grams, right? In fact, you could say grams of what? Yeah, my solute, Na2CO3. Okay, so if you want to, how would you prepare? I would say something like place you got to have a big beaker on a balance. So let's put a big beaker on a balance. Right? Put a big beaker on a balance. Right? One of those mass balances. Right? You should probably tare it. I guess you could say that. Tare it. Okay, so now it reads 0. It's got that nice big beaker on there. Add 25 grams sodium carbonate. Add 25 grams sodium carbonate. Right? Then add blank until 250 grams, until a total or whatever you want to call it. But we didn't tear it again, so until 250 grams is reached. Brandy, add what? Add what? There's only one word in there that gives you the hint. Aqueous. That means we have to add water. Add water. It's the only hint that it gives you. Okay. So most of the questions, though, they are going to stop right here. It's not very often where they ask you, how would you prepare? But I wanted to make sure you got that because that's, I think, one of the toughest questions that can be asked. Okay. Try this one. How many grams of HBr, hydrogen bromide, are in 25 mils of 0.18 big M HBr? Now, big M, you're not supposed to say big M. You're supposed to say molarity, or say, anybody else know? Molar. Big M stands for molarity or molar. Each one will work. So pick the equation. You have 4 choices. You have everything you need to solve for the unknown, and you'll have it. If you're not sure, just ask. Lauren, you see what to do?
Yeah.
Meryl, see what to do? Let's pick on somebody here. Albert, let's pick on you. Is this the equation you used, hopefully? Okay, so what did you substitute in here? Oh, good, 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 good. Okay, what'd you get? 0.025. Now, you can do it the writing out way, but if you've done it so many times, just move the decimal place how many times? 3. But this way, you won't screw up if you do it this way. Okay. So now we're partway there. What else did you substitute in, Eric? Yeah, 0.18 big M. Solve for the moles of solute. So my moles of solute What did you get? Jessica, what'd you get for the moles of solute? The 0.18 times the 0.025. 0.0045? Everybody else get that? Okay, we're good. Now we got to get it into grams. What's the anybody? What's the molar mass of this stuff? 80.9. Okay, now you multiply it and you get 36? 0.36. Several folks got 0.36. Now, if you haven't had me in class before, you write down all this nice work. It looks beautiful. You get the right answer. I'm going to still take a point off because you need units. You need the grams. And you can write grams, or you can write grams of HBr. Right? Either one works. Okay, Summer, did I lose you in that one? Make sense? Okay. Cassandra, how about this one? Number 1. Which of the following ions would be expected to have the greater energy of hydration? Yeah, because of its charge. Okay. Oh, we've got some time here. Okay, well, let's just go in order here. We'll see how far we get, right? We've got a bunch. Try to knock some of these out here, and I'll ask some questions as soon as I give you some time to get it completed. What mass of solution containing 5% potassium iodide contains 258 mg must be milligrams, Ki. So pick the equation. You have everything you need. Keep a little pin over here. Wake up, wake up, wake up, wake up. Anybody get an answer for this one? What'd you get, Romero? That's all right. What'd you get? 5,700? I don't think that's right. 12.9? Anybody else get a 12.9? Brandy's saying 12.9. What'd you get, Eric? 5160? Well, we're getting. You got 51,000 too? 5,000. So you got it, isn't it? All right. So for the mass percent, everybody, we're going to put in the 5. Okay. The mass of the solute. Which one are we solving for? What else? Wow, we're just looking for total mass. So the mass of the solute, you put in 258 milligrams. Now, if we put in 258 milligrams, that means your total mass is going to come out in what units? Milligrams. That's fine. Right? As long as you just keep track and report it. Right? That's okay. Maybe he's right. Okay, we'll find out. Oh, yeah, okay. And we're going to solve for total mass. So solve for total mass, and all right, bring it to the top, bring the 5 down to the bottom. Does that make sense? $258. 258 divided by 5 times 100. Ooh, he's 5,160. Dang. It's because it's in milligrams. That's why, right? That's why it looks so huge. That's why it sounds so funky. If you converted it into grams, it would be what? 5.16. So either answer's fine as long as you write down those darn units, right? It'll work. Okay, let's try this one. Fructose. Sugar, and it's in honey and fruit and stuff. It's the sweetest sugar, twice as sweet as sucrose. How much water should be added to 1.75 grams of fructose to give 0.125 little m solution? Little m is molality. Try to get this one. Pick the right equation. You know 2 out of the 3. You have to. Oh, it's hard to see without writing all the units. What the heck's going on? So then that would be, so you got it into moles. Okay. Yeah, so that's just your moles, though, right? Yeah, yeah, you're getting there. Watch your units. See, if you write more stuff, it'll help you. It'll tell you. Write that initial equation down. Let's write down that initial equation. Hopefully we are picking the molality, equation number 3, right? Molality is moles of solute over kilograms of solvent. Okay. In this question, I think it would be easier if we didn't use the words solute and solvent. We actually stuck in what the stuff was. Little m, moles of what, kilograms of what. Monica, what would you say? Little m is moles of, yeah, solute, but what's the solute? Moles of? What do we put on the top? Moles of? Yeah, except I wouldn't write the word fructose. I would write C6H12O6. It's a lot. It'll be much, and it falls into the format of everything we've been doing. And then kilograms of solvent, Vanessa, kilograms of, what's our solvent? Water, H2O. Okay, now the question wants us to find what, Ramiro? How much water? Does it specify the units, Mari? Usually they say how much water. They'll say, you know, how many milliliters of the what. Do they specify the units that they want their answer in for amount of water? You could use kilograms. It'd be the easiest way, right? But in the question, they didn't say. So I would just leave it in kilograms if you get it, right? I would. You could convert it to milliliters, whatever, but that's going to be a job. So if you get the answer in kilograms of water, you're done. Okay. So Mari, what did you do first? Okay, I did that so that I would identify what the solute and the solvent is. Water is the is always the solvent is always the one that you have more of. And in all these, and there's also kind of a hint saying how much water should be added to 1.75 grams of fructose. So they're really dumping in a lot of water. Water's definitely the solvent. That's okay. Does this make sense so far then? Okay, Caroline, what would you do next then? So in that equation, we have to know two of these. Convert the grams to moles. How many grams do we have? We have 1.75 grams. C6H12O6. I need the molar mass of fructose. What is it? 180? I see a bunch of 180s. Good. 180 grams in a mole. And then I get, did anybody get the number of moles? 0.00972. Did anybody else get that? Okay. So that's our moles. So we know how to plug him in for moles. So my little m is what number? My little m for 0.125. 0.125 has to equal 0.00972 all over kilograms of water. Solve for kilograms of water, and we'll have it. Yeah, exactly. Divide the 0.00972 by 0.125. Ah, 0.125. And the final answer is, Jasmine, what'd you get? .077. How's that sound? 78 kilograms of water. Okay. We finished right on cue there. So there's some more here you can practice on, or you can jump into the homework. Okay. Come by. If you're stuck on anything, I'd be glad to help you out.